This is a video from section 12.2 and it's based off the lecture notes. A vector is a quantity that has both magnitude and direction. The length of the vector represents the magnitude of the vector and the arrow points in the direction of the vector. And so to give you a visual of what we are talking about, I can start here. This can be my initial point A, and I'm going to draw an arrow in this direction. And notice how I stop here at a point which I will call B, right? And we can also represent this vector with a V and an arrow on top, and we'll get into the representations of a vector a bit more. Suppose a particle moves along a line segment from point A to point B. The corresponding displacement vector V has initial point A and terminal point B, and you can see I drew it again down below. Here's A, right? I draw this little line here, and I'm going to put an arrow at the end. And this terminal point is B, and I can represent this by a V with an arrow on top. Okay? So V is also represented by the vector AB. A is my initial point, and B is my terminal point. And by the way, the vector AB is different from the vector BA. So if I wrote the vector BA, what you're in fact telling me is that my initial point is B and my terminal point is A. So order does matter when you represent a vector in this fashion, especially. Okay? Two vectors u and v are equivalent if the vectors have the same length and the same direction. So in other words, two vectors are the same regardless of where they are in space as long as they have the same length and the same direction. Okay? And if you notice, u, which is right here in blue, okay, so this vector u and this vector v are equivalent to each other. And we're going to write that u equals v. They're in different positions, but they're equivalent because both u and v are pointing in the same direction and they have the same length. And so, and that's really important. Both conditions have to hold for them to be equivalent. So in other words, here's a vector u, right? And suppose v went in the opposite direction. Now, they might have the same length, but they are not equivalent to each other because u points one way and v points the other way. So in that example, u does not equal v from a visual perspective. Okay? The zero vector represented by 0 with an arrow on top has length 0. Okay? To add vectors u and v, we have two methods. We have the parallelogram law and we have the triangle law. And we're going to first start off with the parallelogram law. Okay? So these are geometric methods to add vectors. So notice how I drew u and v so they have a common initial point. Okay? And what I did was I formed a parallelogram. Okay? Now, u plus v is the diagonal of this parallelogram, where the initial point starts here. I draw the diagonal, okay? And the terminal point is on the opposite side of the parallelogram. Okay? And I just draw an arrow where the terminal point is. So let me do that again. Suppose I have a vector u, and suppose I have a vector v. It doesn't matter. Okay, so we can put it right here. Now, notice how they have a common initial point. And you might say, well, what if they don't have a common initial point? Remember, two vectors are the same regardless of where they are in space, as long as they have the same magnitude and the same direction. So you would just make them have common initial points. Now, we're going to form a parallelogram. And so notice here, I go like this. And I'm going to connect the initial point of U and V to the terminal point, which lands on the opposite side. That's over here. And so this right here, I'm going to connect these two dots, and I'm going to draw an arrow at this terminal point over here. And I claim this is U plus V. So the diagonal of this parallelogram will be U plus V. And that's how you can add two vectors geometrically using the parallelogram law. Now, what if we want to use the triangle law? Now, notice how I did this very strategically. So we have U here. Now, when I drew V, I started at the terminal point of U and drew V accordingly. So V is in red and comes down here. Now, how do I get U plus V? Well, to get U plus V, I take the initial point of U and connect it to the terminal point of V. And that's what this is. If I can draw this. And then what I do is I draw an arrow at the terminal point of V. So let's do that again, okay? Suppose this is U, and I'm going to draw V. So here's V. So to get U plus V, I'm going to go from the initial point of U to the terminal point of V. So I'm going to connect these dots, and I'm going to draw an arrow at the terminal point of V, which is right here. And so I claim, geometrically speaking, that this is U plus V. And that's how we add vectors using the triangle law. Let's take a look at a scalar multiple of vector V. So, for example, if we take a look at 1/2 V, this is a vector that lies in the same direction as V, but the length is 1/2 the length of V. So what does this look like visually? So I want you to notice something. If I draw V, that's this vector here, I'm drawing over it in red. Okay? Now, 1/2 V is in the same direction as V, but it's half the length. So half the length of V would be roughly here. So if we're looking at this from a visual perspective, and then I'm going to draw half V. So I start here, and I'm going to draw, and perhaps it's about here. And this vector is 1/2 the length of V. Let's take a look at another example. Suppose I had -2V. This is a vector that has twice the length of V, but the direction of -2V is opposite. So let's finish that out. So this is opposite the direction of V, right? So what does that look like? Now, this here is vector V, okay? Now, I want to give you an idea here. So I'm going to go from here to here, and then I'm going to do another one of comparable length. So let's suppose that's about here. Now, if I put the arrow in the same direction as V, this would be 2V, okay? Because 2V has twice the length of V, but V and 2V are going to point in the same direction. But if I start and go the opposite way, so what if I did this? This would be negative 2V. So negative 2V still has twice the length of V, but it's going in a direction that's opposite of V. And okay, that's going to do it for this video. This is section 12.2, and this is a video based off the lecture notes. Okay, thank you.